Joe and Helen Kington, professor in environmental change in the Department of Environmental Sciences at the University of Virginia. And his research is involving the carbon cycle and what that entails in terms of ocean and biogeochemistry and using a combination of field data and satellite, remote sensing, and numerical models. He has been at NCAR and he has been at Woods Hole, and he has also served in the White House OSTP. He has a PhD in chemistry from the University of UCSD and a PhD in chemical oceanographer from MIT. He's a fellow of AGU and the American Association for the Advancement of Science and the Association for Sciences of Limnology and Oceanography. So a very impressive background, and this is a topic we're talking about MCDR today, marine carbon dioxide removal, which is a hot and still somewhat controversial topic. I think this is a topic that many of us have been shying away from for many years, along with other sort of geoengineering approaches. But I think there's also a realization of the fact that Paris, as originally conceived, is simply not working. And if we want to dial back on the greenhouse effect on the atmospheric content of CO2 and methane and other greenhouse gases, we will have to look into everything. And this is a very interesting and potentially promising avenue. So Scott, the floor is yours, and we look very much forward to hearing what you have to say.
Oh, great. Thanks, Lars. And you can hear me okay?
Yep, it is fine.
Excellent. So thanks for that introduction. As I think Lars mentioned, marine carbon dioxide removal is a controversial topic. Really, it comes down to trying to balance trade-offs of how we deal with our emissions of greenhouse gases to the atmosphere. Are there ways to counterbalance emissions by actively removing carbon dioxide, in this case, into the ocean? And then what are the impacts of that? How would we track that? How would we monitor that? And I'm just showing here on the right-hand side of this plot some of the technologies that have been discussed. Nutrient fertilization, which would be a biological approach to stimulate phytoplankton that would take up carbon dioxide by photosynthesis and hopefully export some of that organic matter to the deep ocean. Similarly, seaweed cultivation, where the seaweed would be grown and then sunk in the deep sea, artificial upwelling to bring nutrients up from below, ecosystem recovery to improve degraded ecosystems that might then enhance carbon uptake, and then more technological solutions or geochemical solutions such as adding alkalinity to the ocean or electrochemically adding either alkalinity or actually stripping CO2 out of the ocean. Just to get everybody on the same page, most of you are very familiar with the so-called Keeling curve. That's the long-term measurement of atmospheric CO2. Dates back to the late 1950s. I'm showing here on the left-hand panel the results at the Mauna Loa Observatory that shows that atmospheric carbon dioxide, a key greenhouse gas, has increased by about 50% over the last 70 or so years, and that this increase in atmospheric CO2 and other greenhouse gases like methane and nitrous oxide are associated with a large-scale warming of the planet's surface, shown in the right-hand side, and that over the last 50 years or so, we've seen roughly a linear increase in temperature driven by the mix of greenhouse gases and aerosol effects combined. So then the question is, what does the future look like? And one way of thinking about the future is to compare the cumulative emissions of carbon dioxide that's shown here in the left-hand panel against global mean temperature anomalies. And for the historical period, this is based on observations, there's a reasonably good linear relationship between increasing temperatures and the cumulative CO2 emissions, which makes sense because CO2 is a long-lived gas. About half of what we emit to the atmosphere from fossil fuel burning stays there for decades to centuries, and it accumulates over time. So the cumulative emissions are a pretty good proxy for the buildup of carbon dioxide in the atmosphere. And the colored cones are just showing different climate scenarios for the future, showing that depending upon how much more carbon dioxide we emit, we can expect a certain level of warming, and within some approximations and of course uncertainties, that you can actually estimate how much warming we're going to get in the future based on how much more carbon dioxide we're going to emit. And this has generated this concept of remaining carbon budgets. And so in the black line in the right-hand panel is showing the historical carbon dioxide emissions, which are closing in on about 40 billion tons per year of carbon dioxide. And that, for example, if we wanted to stay below 1.5 degrees Celsius of warming, the green line suggests that we only have about a little more than 200 tons of 200 billion tons of CO2 emissions left. And in order to keep, go from our current emissions of about 40 tons, that gives us only a very short time with a very rapid decarbonization, a very rapid reduction in emissions. If you expand that out to allow, for example, warming to go up to 2 degrees C, over here 2 degrees C on the left-hand panel is somewhere out here with a much larger cumulative CO2 emissions, that gives you a longer time period, a longer remaining carbon budget, but you still need to radically and rapidly reduce emissions in order to get those emissions to zero in time to stabilize the climate at a particular global mean temperature anomaly. I'm not going to go into it too much, but there's a lot of interesting offsets in the Earth system between the climate inertia, the amount of climate warming that's already built into the system because of our past emissions of greenhouse gases, and the carbon inertia that when you emit carbon to the atmosphere, carbon dioxide to the atmosphere, there are natural sinks that remove them. And those two inertias, the climate and the carbon inertia, approximately balance out, which is why there's the focus here on reaching a net zero emissions, that would lead to at least a stable surface temperature. It wouldn't stabilize, for example, melting of the Antarctic or sea level rise. One way of framing this all together is to look at what kind of emissions you would need relative to a no policy scenario, basically no change in climate policy. And so this is some work we've done with folks at PNNL, connected with the University of Maryland, using the GCAM integrated assessment model, where we said, okay, well, we have in this black line is running up on the left-hand side of the plot is the historical global emissions used in the model. A no policy scenario would have increasing emissions over time because of population growth and technological development around the globe. We really need to be on this blue dashed line. The net emissions need to reach zero sometime before mid-century in order to stabilize climate, at this case with a target of 1.5 degrees Celsius warming. And the way you can do that, predicted by different model scenarios, would be a combination in the purple of decarbonization. That would be basically removing fossil fuels from the energy system and replacing them with renewables or other non-carbon emitting, non-greenhouse gas emitting energy technologies, or really advancing the use of carbon capture and sequestration. So you might still be using fossil fuels, but you'd be capturing that carbon dioxide rather than releasing it to the atmosphere. One of the interesting things out of these model scenarios, and this goes back to a comment that Lars made at the beginning of how are we going to reach these Paris targets of 1.5 degrees Celsius or well below 2 degrees Celsius, is that the models say that there's a certain amount of decarbonization that's feasible, but beyond that point, it gets more and more expensive because these go throughout our energy system. Some of the other greenhouse gases come from our agricultural system, and that we might have to live with a certain amount of residual emissions that are very hard to abate. But that these residual emissions could be offset by the residual emissions in light blue could be offset in this sort of orangish color by some amount of carbon dioxide removal. And this carbon dioxide removal would balance out the residual emissions and perhaps even go slightly negative for a time, which would allow us to perhaps overshoot a climate target and then come back to it with time. So then the question is, well, how realistic are these model projections of carbon dioxide removal? And I'm going to focus here today on carbon dioxide removal in the ocean space. There are similar terrestrial-based approaches that are a mix of biological approaches and geochemical approaches. So in terms of what's being discussed, and in some cases actually being advanced by companies, by startup companies and industries, it's really a mix in the ocean of everything from, on the very far right-hand side, a very technological approach. Direct ocean capture and CO2 stripping would be basically you're taking seawater, you're electrochemically splitting that water, forming acids and bases, using the acids to acidify the water to make it basically bubble out the CO2 gas. When you acidify water, you push all the dissolved ions in seawater down here below. So most of the inorganic carbon in seawater is in the form of either carbonate ion or bicarbonate ion. But if you add CO2, you can basically push all of those ions into carbon dioxide gas, and you can strip that out, and then you could remove that and then pump that carbon dioxide down into a geologic reservoir. The latter part, the sequestration, looks very similar to what you'd do if you were doing either direct air capture on land or carbon capture and sequestration from a fossil fuel power plant. Moving over a little to the left, ocean alkalinity enhancement is the idea that one of the reasons why the ocean's so good at taking up and storing carbon dioxide, one of the reasons why there's so much dissolved inorganic carbon in the form of bicarbonate and carbonate ions, is because seawater is alkaline. And so if you could add alkalinity either through electrochemical means or through geochemical means by grinding up alkaline rocks and adding it to the ocean, you could stimulate CO2 uptake. Notice in both of these technological cases, you're not actually removing carbon dioxide from the atmosphere. You're actually removing it, inorganic carbon from seawater in the direct ocean capture case, or you're adding alkalinity in the alkalinity enhancement case, and then you're expecting air-sea gas exchange to compensate and remove carbon dioxide from the atmosphere. And in fact, if you look over more towards the left to the more biological approaches, all of these approaches rely on some re-equilibration of the surface ocean. So there'd be a perturbation to the surface ocean, a drawdown in the amount of CO2 gas in the surface ocean that would then re-equilibrate over time by air-sea gas exchange with the atmosphere. And this ends up being very important because that gas exchange is relatively slow. It's not instantaneous. So the biological approaches, I'm going to talk a little bit more about iron fertilization. This is this idea that over large swaths of the ocean, marine plankton are limited by not just macronutrients like nitrate or phosphate, but they're actually limited by micronutrients like iron. And you could add a small amount of iron and stimulate a lot of phytoplankton growth, and some of that material would then sink to the deep ocean, would actually act to draw carbon dioxide from atmosphere and surface ocean and pump it into the deep sea. You could do the same thing with seaweed aquaculture. And then on the far left side is coastal and ocean blue carbon. I'm not going to talk too much about marshes and seagrass beds and mangroves, but I will talk a little bit about where we are in terms of thinking about degraded ocean ecosystems. All these biological approaches at the end are basically just responding to the fact that photosynthetic organisms remove carbon dioxide to form biomass. But then, of course, that biomass can be respired back to CO2. So unlike the alkalinity case, where if you add alkalinity, you've basically kind of locked that CO2 in for a long period of time, as long as the alkalinity doesn't get removed. With the biological approaches, you need to not only form that organic matter, but then get that organic matter away from the surface ocean, because it will very likely be respired. One of the reasons why coastal blue carbon ecosystems are so effective is they bury a lot of organic carbon in sediments, locking it away from the atmosphere. But in the ocean, almost all of the organic matter that's produced gets respired. It's just a matter of whether it gets respired in the surface ocean or gets respired in the deep sea. So just to give you some ballpark, all of these approaches that have been proposed are acting on top of very large natural cycles. So I'll just go back a few slides. If you look at the magnitude of CDR, we're talking, cumulative between marine and terrestrial approaches, we might need a few billion tons per year. The ocean's already removing, roughly 2.5 to 3 billion tons a year of CO2 from natural processes. So any carbon dioxide removal would be in addition to that. And then one of the problems that makes it very challenging to document and do the verification for carbon dioxide removal is we already have large carbon fluxes within the ocean. We have a large amount of biological production and export flux. And so if you were to be thinking about biological approaches, how would you quantify the perturbation that you've done, the additional primary production and export that's in addition to the amount that's already happening naturally? And there's a lot of variability on the natural cycle as well, and that needs to be taken into account. Similarly, there is a large uptake of anthropogenic CO2. I'm showing here the most recent estimate is about 2.9 plus or minus 0.4 billion tons. And so anything we do on the geochemical side or the biological side needs to be done recognizing that there's already a large perturbation going on because of the rise in atmospheric CO2. The ocean's a good sink for that CO2 anyway. And would we actually be able to see these carbon dioxide removal signals on top of this large background? So I'm going to focus my talk primarily in this sector on geophysical feasibility, things like efficacy and additionality. Additionality is simply that, can we show that it's actually, you've actually changed the system so the net effect on the ocean is to increase carbon dioxide uptake. Some of the things you could do might locally change carbon dioxide uptake, but on an ocean scale or a basin scale would have a much smaller effect. Durability or permanence is how long is that carbon dioxide locked away from the atmosphere. And for policy decisions, we want multi-decade, century, or millennial scales, not just a change over a year or two or storage over a year or two. So durability or permanence is really important. Scalability, it's one thing to do things in a lab, or it's one thing to do things from a research ship. But if we're going to scale these up to hundreds of millions to even billions of tons of CO2 per year, these approaches need to have technological feasibility to scale to much larger levels. And then monitoring, reporting, and verification are all critical if we're going to actually include this as part of climate policies. There are, of course, environmental issues, technological issues, social and institutional issues, a little bit beyond the full scope of my talk, but these all come with potential trade-offs if you look around the rest of this wheel. And sometimes the barriers to implementation are, we might be able to show that geophysically that this might work, but that the environmental trade-offs or challenges are too large, or the economics are too expensive, or there's just not social or cultural acceptance of these approaches because of the large scale impact they're going to have on the ocean. So just to give a little example, we'll start with ocean alkalinity enhancement. So this is basically adding, in this case, some material, alkaline material that would change the chemistry of seawater. In the process, you add alkalinity. So on the right-hand side, this is a small scale, large eddy simulation that I borrowed from some of Katja Fennell's work, where you see this stripe and mixing of alkalinity. You'd be adding alkalinity either from the shore or from a ship. In the places where you add alkalinity, you drive down the partial pressure of CO2. So PCO2 is just the partial pressure of carbon dioxide, and that reduction in the partial pressure of carbon dioxide is what drives the air-sea CO2 flux. So far, by adding alkalinity, you haven't actually removed any carbon dioxide from the atmosphere. This chemistry happens very quickly. That carbon dioxide then has to be replaced over time by uptake of carbon dioxide from the atmosphere, which would bring this PCO2 value back towards atmospheric values. On these very small scales, there's lots of technological issues. If you add too much alkalinity, you can actually precipitate other minerals that will strip that out. So you have to worry about how quickly you release it, how quickly it's being mixed away from the release site. In terms of monitoring that, you could think of, if you were adding it from a ship, you might have approaches using moorings or autonomous profiling floats, surface drifters, gliders, ship surveys, where you've added a certain amount of alkalinity, and over time that alkalinity disperses. And that alkalinity will have geochemical effects, right? We're trying to track how it's changing surface the partial pressure of carbon dioxide in the surface ocean, use that to monitor uptake and air-sea CO2 fluxes. But the green dots here are phytoplankton and other marine life. We'd also want to make sure that adding too much alkalinity doesn't have negative impacts on marine life. And at some point, this patch is going to be so dispersed that you're going to have to combine field measurements with some form of numerical modeling. And this is just to show, this is the plan view, this is the horizontal view from above, that these plumes are going to be dispersed, and a lot of work has gone into how would you use other chemical tracers or numerical models on small scales, perhaps chemical dyes, to track where the plume goes. On larger sort of mesoscale scales, this is some work that Darren McKee has been doing, looking at using Argo float data and satellite data of sea surface altimetry. You can actually watch, if you add, for example, the blue square in that upper right-hand panel is a box, order of about order a little less than 1 degree of latitude and longitude on the side. If you were to add alkalinity on that scale, it's going to be stretched and transported and stirred and then eventually mixed away and dissipated by the mesoscale circulation. So one of the real challenges, unlike some projects on land for carbon dioxide removal, is of course the ocean is turbulent, and you can't go back to the same spot in the ocean You can't just take latitude and longitude coordinates, go back 5 years later, and expect to see the signal. That water is then long gone. And in fact, over relatively short periods of time, unless you continue to add alkalinity, the alkalinity anomaly is going to be dissipated. And so that's where you're going to move from a combination of field observations to numerical models in order to track the long-term evolution of the alkalinity that you've added. Now, this dispersion is happening on the timescales of days, where gas exchange timescales are more like, for carbon dioxide in particular, because of the chemistry of the acid-base dynamics of seawater, the timescales for reequilibration of surface water are quite long. They're order months and in some cases years. And so the left-hand column is just showing some results from some numerical experiments for alkalinity enhancement using a relatively coarse resolution global model, where if you added high alkalinity along the coastlines, you'll see the alkalinity move into other parts of the ocean over time. So the blues are high alkalinity additions down into the reds, and you'd have fairly wide regions of air-sea gas exchange. And you can see these plumes where in some cases, for example, off Japan, where you have the Kuroshio, or off the Gulf Stream, that even if you added alkalinity near the coast, the effective removal of carbon dioxide from the atmosphere associated with that alkalinity might happen weeks or months later, long distances away from where you added the alkalinity. The other factor, and this is now moving over into the right-hand panel, is that for alkalinity enhancement to work, the alkalinity needs to stay at the surface ocean. If the water gets subducted into the ocean interior or gets mixed by deep convection, you're going to have a very low efficiency. And so this is just showing a plot from the seaworthy group of the efficiency of the change in dissolved inorganic carbon after some time period relative to how much alkalinity you added. And this is on a window of 5 years, and you can see at some high latitude spots and deep mixing spots, you have very low efficiencies. So we need to take into effect ocean circulation, not just locally where we're doing the perturbation, but on long time scales as the signal moves away from the release site. And as I had mentioned, all of these perturbations to air-sea flux are going to be on top of a large background. So for those not familiar, there is large geographical variations where the equatorial regions, for example, here the equatorial Pacific, because of upwelling of carbon-rich water from below, have a net release of carbon dioxide to the atmosphere, and then blue regions are where there's uptake. So even though on a global scale, the ocean's taking up anthropogenic carbon dioxide, on any particular location, there's large geographic variations and also seasonal variations that are a combination of ocean warming and cooling that affects solubility, biological activity with that seasonal variability, and also large-scale circulation. We can see this long-term uptake of anthropogenic CO2. This is one of the longest, this is the Bermuda Atlantic Time Series site. One of our more robust long-term data records goes back a few decades, and you can see that the amount of dissolved inorganic carbon, that's what DIC stands for in the upper panel, or anthropogenic CO2 in the lower panel, that the amount in the surface ocean has gone up with time. There is considerable month to month and even year to year variability in that. It takes a long time record to track even that very large uptake on a global scale from rising anthropogenic CO2 levels in the atmosphere. So any particular carbon dioxide removal approach, even if you went back a few years later and you said, oh, look, there's more dissolved inorganic carbon in the water now than there was when I did the perturbation, you'd have to say, well, how much of that is because of this long-term background natural process of uptake versus the actual carbon dioxide removal process that you've implemented. And this is just showing that that challenge gets even more difficult at depth. So this is my favorite ocean transect from Iceland down to about South Georgia in the Atlantic. So it's in the Eastern Atlantic, and then transitions to the Western Atlantic and the South Atlantic. And this is showing in the upper right-hand panel, showing dissolved inorganic carbon as a function of depth. And so if you're an oceanographer, you immediately look at that and say, oh, I can see water masses that have different origins. They have different dissolved inorganic carbon amounts because of where they were formed and the history as they've been moving over decades to centuries through the ocean, and trying to reconstruct in the lower panel the amount of anthropogenic carbon that's been taken up. Notice the top scale has bounds of sort of 1900 to 2200. Anthropogenic carbon this is the change over time, is about 10 to 15 micrograms per kilogram per decade. So it's a pretty small signal relative to the background and the large geographic variations. And it takes a lot of effort to document long-term changes in dissolved inorganic carbon in the ocean, which will make verifying carbon dioxide removal also challenging. And then finally, just to wrap up the alkalinity enhancement example, you also need to put on your engineering hat and think about the life cycle analysis, right? So if you were to spread enough alkaline material to take up 1,000 kilograms of CO2, that's not the full story, right? Because you had to, let's say if your alkaline material was calcite, you start with limestone, it's going to take a certain amount of energy, and there are CO2 emissions associated with mining. And then you need to crush and grind it to a small enough scale so it's chemically reactive. It turns out that adding limestone, the kinetics of limestone dissolution is really slow. So most approaches have assumed that you then take the limestone and you actually do a calcinization step. You actually heat it at very high temperatures and drive off a lot of the CO2 to form lime, calcium oxide, that then can be added back to the ocean. So rather than directly adding calcite, you're actually adding lime. But a lot of that CO2 that's been driven off then needs to be captured, and you have to capture it effectively, and then you're going to use energy to compress that CO2 gas. The CCS is carbon capture and sequestration. And then, of course, you're going to have to transport this out to sea and spread it. So out of all, you're going to add enough alkaline material to soak up 1,000 kilograms of CO2, but almost half of that CO2 is going to be compensated because of all the CO2 you needed that gets released during the life cycle associated with collecting the material, calcinization of the limestone, carbon capture and sequestration, transport. And so for any of these techniques, you need to think about a full life cycle analysis. So not just what the technique does at the perturbation source for the ocean, but the full engineering life cycle analysis. And I'm just throwing in this in for completeness. There have been a variety of approaches where people have looked at, for example, scalability. So alkalinity enhancement does look like it has the potential to scale. It's relatively expensive because you have to collect the materials and process the materials. We think the efficacy is pretty high because you're changing seawater chemistry in a known way. Fairly good durability. Relatively low monitoring, measurement, reporting, verification challenges, because as long as the water stays near the surface, we're pretty confident that the chemical reactions that are occurring in the air-sea gas exchange are going to occur. And then social considerations, more mining, energy use, ocean dumping, lots of concerns there. And then the environmental risk, we're still understanding how adding large amounts of alkalinity would affect marine ecosystems. And unfortunately, a lot of these alkaline sources also bring with them trace metals, and some of which can be toxic at fairly low concentrations. And then, of course, there's mining impacts on land. So you need to look at that whole spectrum, not just does it work in a model or in a small pilot experiment, but look at what would happen if you were to do this at scale. I just want to work through couple more of the biological examples. These have gotten a lot of discussions over time. So the iron fertilization approach is basically the idea that, we know that there are phytoplankton in the ocean that are very good at photosynthesizing, taking up carbon dioxide. Only a small amount of the photosynthetic carbon that's produced actually makes it out of the surface ocean into the deep sea. The vast majority is respired by zooplankton or bacteria or even fish or marine mammals. So there's a rapid recycling of carbon dioxide and organic carbon in the surface ocean, and a biological approach has to disrupt this by somehow increasing the amount of material that's export into the deep sea, where the deeper you go in the water column, the longer you are trapped away from the atmosphere. And so there was a series of field experiments conducted over the last couple of decades where people have done mesoscale experiments to add iron or other nutrients to the sea. Iron limitation is only in limited places. So these are places where you have a substantial amount of nitrates. So the color contour on the left-hand panel is the surface nitrate concentration. So you'd need to go someplace like the North Pacific. There's a little bit of limitation in the equatorial Pacific or the Southern Ocean. So these are often pretty harsh places to work. And the experiments, these were heroic field experiments, but even those didn't last long enough to give us a full picture of how the ocean's going to be affected on long time scales. So this is just showing the Soirée experiment where iron was added and there was a rapid increase in chlorophyll. So the orange is the accumulation rate, basically the effective rate at which phytoplankton are growing. And you saw chlorophyll increased by about a factor of 5 over a few days. You got a very clear signal in surface ocean chlorophyll that you could see from space. It's much harder from these experiments. Not all these experiments tracked carbon dioxide export or effects on long-term air-sea gas exchange, but there have been modeling studies that have built from these work. This is just showing some work by folks out at UCLA, showing, for example, this is the equatorial Pacific. So here's North America in black, Baja California. In the model, there's a band of high chlorophyll along the equatorial Pacific because it's a region of equatorial upwelling. They in the model, added iron to this small little box. You got a burst of chlorophyll. You got a positive chlorophyll anomaly where you added iron and increased primary productivity. And then if you look down here below, you actually draw down, there's typically a lot of nitrate that's brought up by equatorial upwelling. You got a large drawdown of nitrate, and that reduced nitrate actually was advected out of the region. So one of the things that people worry about with some of these biological approaches are downstream effects, and this gets to that concept of additionality. So if you add iron and basically remove so much nitrate that you might stimulate biological productivity in one place, but reduce it somewhere else downstream, the overall effect might not be as big as you think, right? Because you have downstream consequences for the marine ecosystem. The other factor is that, as I had mentioned, very little of the organic carbon, only a small fraction, something around 10 to 20% of the organic carbon that's produced by photosynthetic organisms gets export from the surface layer. And so if we say the surface layer is approximately 100 meters depth here on the y-axis on the left-hand side, if you look at the sinking particulate organic flux, almost all of that organic carbon gets remineralized in the upper 400 meters or so. And so if you're starting to think about how long that organic carbon is going to get locked away, people have done tracer experiments, numerical experiments, and looked at what's the fraction of carbon dioxide retained after 50 years. So if you were to do an experiment, say here in the equatorial Pacific, after 50 years, only about half or a little less of the carbon that was originally removed would be retained in the ocean, because the carbon dioxide, the organic carbon sinks, it gets remineralized to carbon dioxide, and then the circulation brings that back up to the surface where it's ventilated to the atmosphere. And in fact, over much of the ocean, the fraction is actually pretty small. And so in some ways, stimulating the biological pump is not the most effective, because you're not actually transporting it deep enough in the water column, which is in part why people have talked about doing seaweed aquaculture, where instead of allowing natural processes to sink that organic carbon into the deep sea, you'd actually mechanically package it up, make it dense enough so it would sink all the way to the bottom, and avoids remineralizing in the upper kilometer or so, where you have fairly rapid processes that bring subsurface water back to the ocean surface. And then I'll just touch on one more topic, and then stop and take questions. There's also been a lot of discussion about ecosystem conservation, and we know that stopping the degradation of coastal blue carbon systems, these are marshes, mangroves, seagrass beds, conserving the existing blue carbon ecosystems is a really good idea, right? You have a lot of a lot of organic carbon in these systems that, if you degrade the system through development or dredging, coastal habitat destruction, it releases a lot of that organic carbon, and that can be respired and turned back into carbon dioxide that will vent to the atmosphere. Restoring those coastal blue carbon ecosystems also has a lot of benefits, both from a carbon sequestration side, but also from ecosystem services. They provide shoreline protection, enhance biodiversity, enhance fisheries, lots of good things. So the restoration actually turns out to be more expensive than I think some people originally thought. A question that's come up from the oceanographic side is, well, what about away from the shoreline, when we start looking at degraded kelp beds or fisheries that have overfished regions? What could we do? And so the first thing you might want to do is say, well, how well do we understand how much carbon is stored in marine biota? And it turns out, first, it's not a lot. Remember, we were talking about billions of tons of carbon per year in terms of carbon dioxide removal. The sort of range of estimates for all the biomass in terms of carbon is only about a few petagrams up to maybe 6 petagrams of carbon per year. There's a pretty large uncertainty there, but storing or just enhancing the storage of organic carbon is probably not going to be that effective. What you'd have to do is somehow get a change in the biology such that carbon is being transported into the deep sea. So it's not just a rebuilding fish stocks or marine mammal stocks. There's just not enough organic carbon there to have a big effect on a global scale over a long period of time. I would say that one of the really interesting things is These are all, each one of these bars are estimates from different groups of different things. So the tan bar is all ocean biota, green is phytoplankton, zooplankton, all marine animals, and fuchsia, all marine fish. Those all tend to roughly agree, but there have been some papers with a few estimates that are very, very high for mesopelagic fish. These are fish that are living down a few hundred meters or deeper in the open ocean, a very unexplored region. So there have been some papers out there with very large estimates that are hard to reconcile with a lot of what we know about ecosystems. And then if you start to compare the fluxes, so not just the biomass stock, but the fluxes, I had mentioned the carbon biological pump, that iron fertilization would increase the amount of the biological pump of carbon into the deep sea. That's roughly order 10 billion tons of carbon per year. Zooplankton and fish account for about half of that. Fish a smaller amount, and there's a very large uncertainty in how much fish. And so if you start thinking about restoring degraded fisheries, it's likely you have a pretty small lever that right now, or even in the pre-industrial state, epipelagic fish that we typically remove from the ocean by fish stock, wasn't doing an awful lot. Most of the cycling is either microbial or by zooplankton, which are much harder to get to. As I said, there's huge ranges on mesopelagic fish associated with uncertainties, but it's not, we still need to figure out reasonable bounds on that. And then when you get to, for example, marine mammals and great whales, there's been a lot of discussion about recovery of whales, and certainly recovery of whales is a conservation, great conservation success story, but it's not likely to play a big role in terms of the global carbon cycle because of the very small impact they have on carbon cycling. And then this is just showing the same sort of plot for nutrient fertilization and ecosystem conservation, where, for example, ecosystem conservation, we have a pretty low confidence in the efficacy, but for some, like preservation, we might want to do it anyway because of all the other co-benefits. And for iron fertilization, relatively low price for spreading, for example, iron, but considerable challenges for monitoring, reporting, and social considerations and environmental risk. So to stay on time, I'll stop there. It's 10 minutes of the hour, and take questions.
Thank you. So to ask a question, can you all just either raise your hand to unmute yourself or put your question in the chat? I think Anne was first. Go ahead, Anne.
Hi, Scott. Nice talk. You pointed out that some areas are much more efficient than others for the alkalinity enhancement, and then you said there was a very long time period of reequilibration with the atmosphere. Wouldn't that suggest that the best place to put the alkalinity would be in the zones where we're seeing degassing now? So we wouldn't have to wait for the reequilibration into the water. We would just reduce the PCO2 by adding alkalinity, say, in the upcoming areas.
I mean, there is some overlap there because some of the upwelling regions that are degassing are not near subduction zones, but you can think of it as this is a perturbation on the background. So whether you're reducing outgassing or increasing uptake, the question is how big is that perturbation? And so the longer that water stays in contact with the atmosphere, the bigger the perturbation, the bigger bang you get for the amount of alkalinity that you've added. Now, there are some thermodynamics and temperature effects that people have factored in, but yeah, I mean, I think the reality is a lot of, if we were going to do this at scale, it's going to be primarily coastal because, adding, the additional step of going onto a ship just adds transport costs, it adds greenhouse gas emissions. And so, there are already experiments going on tied in with, desalination plants, coastal wastewater treatment plants where you're already pumping a lot of seawater. There are some programs going forward that are coastal based because you need, they're electrochemical, so you need power. So I think, we do need to understand a lot what's the fate of water and alkalinity if we add it. But I think in the short term, a lot of the focus is going to be on coastal because that's logistically where it's going to be relatively straightforward to do.
Great, thank you.
Dr. Lee, you can go ahead and ask your question. Oh, but you're muted. Let me send you a request.
You hear me now?
Yeah,
Yes,
I can
we
hear you
can.
fine.
Yeah, okay, good. Thanks, Scott. Very interesting talk. In one of your slides showing the almost like a decadal change of dissolved carbon from year to year since 1980s. And I saw there was a kind of a, I'm not sure, so sure, I want to verify if it's a interdecadal change associated with such climate mode as El Nino. But I also noted that in the last 10 years, there are quite a consistent upward trend. So I wonder anything changing in the last few years and no such, in annual changes. But before then, I want to verify if it's El Nino phenomena in the carbon uptake.
So that time series is off Bermuda. That's the Bermuda Atlantic time series. That's one of the longer. So there is an INSO signal there, but there's also an NAO signal. And we can argue about the Atlantic decadal signal. I think one of the challenges, I guess rather than focus on that exact time series, because that's sort of the reason I showed that is that we're already spending a lot of effort, a lot of scientific effort, a lot of observational effort just to track the background natural ocean carbon cycle and the impacts of anthropogenic CO2. And so, as you said, there's seasonal cycle variations, interannual, perhaps decadal, that we're already really challenged to decipher. So if we're going to start doing carbon dioxide removal, we need to think about clever ways of how we would be able to do the verification of that carbon dioxide removal, knowing that the background is not constant. And so it makes the counterfactual very, if you're an economist, it makes the counterfactual very hard. What would the ocean have done if I hadn't added alkalinity?
Very interesting part. Thank you.
Jim, you're next. I think you're muted.
Yeah, so I'm wondering about the potential for carbon sequestration in restored oyster reefs. And for example, I understand that in North Carolina, they're quarrying limestone and dumping huge amounts of limestone rubble off the coast to bootstrap restoration of oyster reefs. And if I understand correctly, the limestone would also have an alkalinity effect. Thanks.
Yeah, so one of the questions is how quickly that, if you were to just take large chunks of limestone, the kinetics of dissolution are pretty slow, right? We know that, coral reefs are made out of calcium carbonate. There's lots of limestone, shorelines that are made of limestone. And so the kinetics are pretty small. As I said, one way of getting around it is grinding it up very fine. So you increase the surface area that would increase the dissolution. But even that, the kinetics can be pretty slow. And that's why a lot of groups and modeling studies have looked at chemically altering the limestone to make it more reactive. But of course, that comes at pretty high expense in terms of cost and energy and things like that. I think, there's lots of good reasons to stimulate and rebuild oyster reefs. But on its own, I'm not sure that, carbon sequestration, because as the oysters grow, they actually are taking alkalinity out of the water. So the limestone you put in might be dissolving, but if the oysters are taking it up to make their shells, you might not even be adding net alkalinity to the ocean. But of course, restoring oyster reefs is really important for all sorts of other reasons.
Okay. Thanks. I guess I was more focusing on the calcium carbonate that goes into the seashells and
Well, yeah, that's what I'm saying.
doesn't that sequester
No,
carbon?
actually, because when you form calcium carbonate from seawater, you're actually removing alkalinity. And this is sort of the perverse aspect of seawater chemistry. You might think, oh, by building an oyster shell, I'm storing carbon. But on the sort of century to millennial scale, what you do is you actually are making the water bubble. You're basically increasing the amount of carbon dioxide in the water. So you'll actually outgas carbon dioxide from the ocean to the atmosphere. So you're storing carbon in the shell, but the net effect on the atmosphere is to increase the amount of carbon dioxide. So it's the reverse of what you want to do.
Okay, thanks.
This is why nobody likes chemistry, because it doesn't always do what you expect it to do.
Do we have any other questions? You could also, you don't have to raise your hand, you could just type in.
That looks like about it. Well, thanks everybody. I hope you enjoyed the talk.
Yeah.
Oh, Lars.
Yeah,
Okay.
no, I just wanted to say thanks for a very interesting talk. I need to run off to another meeting now, but this was a great overview. It's actually the first time I've heard this whole topic covered in such a sweeping way. So thank you very much for that.
Oh, you're welcome.
Yeah, thank you. Thank you, Scott. And thank you everybody for coming and joining us this week. Our seminar series will continue next week. Let's just give another virtual round of applause for the speaker. And we will see you all next week. Thank you.